Hello, and welcome to the Digital Technology Merit Badge course. My name is Andy, and I'm a former registered Merit Badge counselor for the Buffalo Trails District and the Lincoln Heritage Council. I've designed this version of the Digital Technology course to be completed by Scouts with their troop for other Merit Badge counselors. Let's enter the world of digital technology. First, we're going to start with our requirements. So there are some requirements that I will not be able to cover in this video, but they are provided online. So the first one is viewing the personal safety awareness video with your parents' or guardian's permission at the link below, and I'll put the link in the description as well. Then for requirement 2A, we're supposed to give a brief history of the changes in digital technology over time. We're supposed to discuss how digital technology in your lifetime compares with that of your parents, grandparents, or other adults' lifetime. And then describe what kinds of computers or devices you might imagine would be available when you're an adult. Then we're going to explain how text, sound, and pictures are digitized for storage. Describe the difference between lossy and lossless data compression and give an example where each might be used. Describe two digital devices and how they are made more useful by their programming. Discuss the similarities and differences between computers, mobile devices, and gaming consoles. Explain what a computer network is and the difference between a local area network, or LAN, versus a wide area network, or WAN. Then we're going to do the following. I'm going to explain what a program or software application or app is and how a computer uses a CPU, central processing unit, and memory to execute it. We're going to name 4 software programs or mobile apps you and your family can use and explain how each one helps you. Then we're going to describe what malware is and explain how to protect your digital devices and the information stored on them. Next, we're going to describe at least 2 different ways data can be transferred through the internet. Then we're going to use an internet search engine to find ideas about how to conduct a troop court of honor or campfire program. And then we're going to use a web browser to connect to an HTTPS secure website with parent or guardian's permission. And then explain how to tell whether the site security certificate can be trusted and what it means to use this kind of connection. Requirement number 6 will not be covered in this course. This is where you're supposed to do 3 different projects that are digital in nature. One of them is exactly what I'm doing now. You're making a PowerPoint presentation with recorded notes or video, and you would put it on a USB drive and bring it to your counselor, and your counselor would see you transfer it from the USB to the computer. So in effect, we're kind of doing part of it, or at least I'm showing you how to do part of it, but we're not going to really cover it in full. For requirement 7, we're going to explain how what each of these protections are and why they exist. So we're going to explain copyright, patents, trademarks, and trade secrets. Then we're going to explain when it is and is not permissible to accept a free copy of a program from a friend. Then we're going to discuss an article or a report on the internet about a recent legal case involving intellectual property dispute. For requirement 8, we're going to do 8A and 8C. So we're going to describe why it's important to properly dispose of digital technology, and we're going to list at least 3 dangerous chemicals that could be used to create digital devices or used inside a digital device. We're also going to do an internet search for an organization that collects discarded digital technology hardware or devices for repurposing or recycling. And we're going to find out what happens to that waste. For the last requirement, 9, we're going to investigate 3 career opportunities that involve digital technology. We're going to pick one and find out the education, training, and experience required for this profession. Let's start at the beginning of digital computing. Early digital computers were electromechanical, using electrical switches to drive mechanical relays to perform calculations. Some of these include the Z series of computers by Conrad Zuse. Conrad's first computer, the Z1, was a fully mechanical, motor-driven computer designed in the home of Conrad's parents. It used binary to do arithmetic calculations and read instructions from punched celluloid film. It was built in Germany in 1938, and it and the plans for it were destroyed in World War II. He improved upon his computer with the Z2, which used electrical relays in place of the arithmetic and control logic. You had to use punch cards to program it, and it could only read 64 words. After the Z2 was shown at a presentation for Deutsche Versuchsanstalt für Luftfahrt, German Laboratory for Aviation, in 1940, the DVL greenlit funding for the Z3. Zuse built the Z3 in 1941 and the Z3 proved to be more reliable than both of its predecessors. The Z3 was able to handle basic exception handling and added the square root instruction. The main goal of Zeus was to build a machine that would help facilitate his work as a civil engineer. The Z3 operated like a stack machine, which is a machine that pushes temporary short-lived values to and from a push-down stack. The Z3 had a stack of two registers, R1 and R2. An example of how it would be used is that a program would load the contents of a memory location into R1, and the next load would go into R2. A store operation would store the contents of R1 back into memory and clear R1, and the next program load would write back into R1. The Z3 lacked a conditional branch instruction, and it would not be until much later in 1998 that Raul Rojas would prove that the Z3 was Turing complete. However, it only meets the definition by speculatively computing all possible outcomes of a calculation. And when I say Turing complete, I mean that a machine can solve any computational problem. Zeus also independently built his computers on the groundwork of converting Boolean algebra into electronic relays, not knowing that the American Claude Shannon had introduced this idea back in 1937. Other digital computers that were being built during this time didn't rely on electrical relays, but rather thermionic valves or vacuum tubes. The first computer to use vacuum tubes was the Atanasoff Berry computer, or ABC computer. Conceived of and designed for solving linear equations by Iowa State College professor John Atanasoff with the help of graduate student Clifford Berry in 1937, it was successfully tested in 1942. Its intermediate storage system, a paper card reader and writer, wasn't fully perfected before John went to work on projects for World War II, and as a result, work on the machine was discontinued. The ABC computer was neither programmable nor Turing complete like the Z3, but it did pioneer important elements of computing, such as binary arithmetic and electronic switching elements. The Colossus is actually a set of computers that were developed between 1943 and 1945 by British codebreakers to help in the cryptanalysis of the Lorenz cipher. It was designed by George Flowers from the General Post Office, from plans by Max Newman at the Government Code and Cipher School at Bletchley Park. The computers were kept secret until the mid-1970s, and as such, did not influence future computer systems. The ENIAC was the first digital programmable electronic computer built by American physicist John Mauchly, American engineer J. Presper Eckert Jr., and colleagues at Moore School of Electrical Engineering at the University of Pennsylvania. It was a government-funded project that started in 1943 with the goal of computing values for artillery range tables. It used plug boards for communicating instructions to the machine. Once programmed, it ran at electronic speed, which was much faster than punch cards or celluloid film programming. The downside to this is that it could take several days to reprogram the machine for a new problem. Like the Colossus, it had conditional branching. So, if it said x was less than 15, it would go to line 23. It was completed in 1946 at a cost of $400,000, which in 2024 dollars would be $6,741,670.33. ENIAC could run at about 500 flops or floating point operations a second. To compare that to modern supercomputers, Frontier, which as of December 2023 is the world's fastest supercomputer, can run at 1.1 exaflops, or 10 to the 18th power flops. The EDVAC was the successor to the ENIAC with two big changes. It was binary rather than decimal, and it was designed to be a stored program computer. A stored program computer is a computer where the data and the software reside in the same memory, which is called the von Neumann architecture. The ENIAC's inventors proposed EDVAC in 1944, and they were awarded the contract in 1946 with an initial budget of $100,000, which is $1,615,417.58 in 2024 dollars. It was completed in 1949 and delivered to the Ballistic Research Laboratory. It had a memory capacity of 1,024 44-bit words, or 5.6 kilobytes in modern terms. The computer had 5,937 vacuum tubes, consumed 56 kilowatts of power, and covered 490 square feet of space. The IBM 650 magnetic drum data processing machine was the first mass-produced computer and the first computer that turned a profit. The first one was installed in 1954, and it was one of the most popular computers of the 1950s. The purchase price for a bare IBM 650 in 1959 was $150,000, or $1,597,102.27 in 2024 dollars. The IBM 650 was considered a relatively inexpensive computer and was popular for teaching college students programming. The 650 was a two-address bi-quinary coded decimal computer. Both data and addresses were decimal, with memory on a rotating magnetic drum. Character support was provided by the input-output units, converting punched card, alphabetical, and special character encodings to and from a two-digit decimal code. The 650 was clocked at the frequency of 125 kilohertz. It could add or subtract in 1.63 milliseconds, multiply in 12.96 milliseconds, and divide in 16.9 milliseconds. The average speed of the 650 was estimated to be around 27.6 milliseconds per instruction, or roughly 40 instructions per second. The basic 650 system consisted of three units. The IBM 650 console unit housed the magnetic drum storage, arithmetical device using vacuum tubes, and the operator's console. The IBM 655 power unit, the IBM 533 or IBM 537 card read punch unit. The IBM 533 had separate feeds for reading and punching. The IBM 537 had one feed, thus could read and then punch into the same card. It weighed between 5,400 and 6,263 pounds. I'm going to skip ahead a few years and go to some of the first microprocessing computers. And I want to start with the Apple I. So one of the main innovations of the Apple I was that it included video display terminal circuitry and a keyboard interface on a single motherboard, allowing it to connect to a low-cost composite video monitor instead of an expensive computer terminal, which is what most computers used at the time. Contrary to the popular belief, it was not the first personal computer to include such a video output, but it was one of the more popular ones. To use the computer, a user supplied composite monitor and ASCII encoded keyboard needed to be connected. If a monitor was not available, a standard television set could be used along with a radio frequency modulator. In comparison, computing machines generally required an expensive dedicated video display terminal or teletypewriter. This, combined with its single-board construction, made the Apple I an elegant and inexpensive machine for its day. An expansion included BASIC interpreter, allowing users to utilize BASIC at home instead of at institutions with mainframe computers, greatly lowering the entry cost for computing with BASIC. The IBM PC and PC Compatible was released on August 12, 1981, and it's the IBM PC Model 5150. It's the first microcomputer in the IBM PC line and the basis for the IBM PC Compatible. The computer was based on open architecture, which means users could add, upgrade, and modify it easily with other computers. This computer had a substantial influence on the personal computer market. I mean, we had beige boxes up until the 2000s, and the internals were just much improved. It only really faced competition from the Apple Macintosh line, although Commodore and Atari were also distant competitors to the IBM PC. This PC came with an Intel 8088. The IBM PC debuted on August 12, 1981, after a 12-month development cycle. Pricing started at $1,565 or $5,309.93 in 2024 dollars for a configuration with 16 kilobytes of RAM, a color graphics adapter, keyboard, and no disk drives. The price was designed to compete with comparable machines in the market. For comparison, the Data Master, announced 2 weeks earlier as IBM's least expensive computer, cost $10,000. Sales exceeded IBM's expectations by as much as 800%, with the company shipping as much as 40,000 PCs per month. The IBM PC used entirely off-the-shelf parts, meaning that IBM did not develop any of the pieces of hardware themselves, specifically for the IBM PC, and you could just buy the parts outright from other vendors. The base factory configuration included an Intel 88 running at 4.77 MHz, 16 kilobytes or 64 kilobytes minimum of RAM, which was expandable to 640 kilobytes, an IBM monochrome display adapter or IBM color graphics adapter, an IBM Model F 83-key keyboard with 5-pin connector, a single programmable frequency square wave with built-in speaker for sound, and for storage up to two 5.25-inch single or double-sided full-height floppy disk drives, and a port for attaching to a cassette tape recorder. It initially didn't have a hard drive option, but that was an option that was added later. And then for expansion, it had 5 62-pin expansion slots attached to an 8-bit CPU I/O bus. and it had optional serial and parallel ports for communication. Requirement 2A continued. How computers were in my time, the 1990s, my parents' time, the 1960s, and my grandparents' time, the 1930s. As this is personal to each and every one of you, I will tell you all my experience as an example. My parents were in their 40s when they had me back in the 1980s. So my parents' time, computers were going from room-sized IBM computers to microprocessor computers such as the Apple I and TRS-80, although they were not aware of computers until the 1990s when I begged them to get me one. My first PC was the Tandy 1000, which is in the picture on the slide, running MS-DOS 5.0. I cannot remember if it had a hard drive or not, but I'm leaning on saying that it did not because I remember having to load a 3.5-inch floppy disk into the floppy disk drive before I turned the PC on so that it would load MS-DOS. I remember playing some classic DOS games like Wheel of Fortune, Einstein Junior's Classroom, and Tandy Diskmate, which was kind of like a Windows 2.0 clone. My grandparents were farmers and would not have known anything about digital computers, even though they were contemporary with when the Atanasoft Berry and Z1 computers were being developed. So also in my time, I saw the rise of Windows 3, 3.1, Windows 95, 98, Windows Millennium Edition, and Windows XP. Computers in my time were a lot of beige boxes. It wasn't until Apple released their multicolored iMacs in the late 90s that we actually got color and variety. And I remember using a computer lab full of Bondi Blue iMacs when I was in middle school. So that would have been back in like 1990, 2000. Requirement 2B. Describe what kinds of computers or devices you might imagine might be available when you are an adult. So to describe what kinds of technology we were going to have available as an adult, I'm going to go put myself back into the shoes I was in 25 years ago when I was in scouting as a child. At the time, the latest computers were running Windows 98 and Pentium 3 processors were blazing fast. ATI and 3DFX graphics cards were all the rage, but I wouldn't come to learn about video cards until I was about 15 or 16. Based on my childhood experience with computers, I expected that they would continue to get faster and follow Moore's law, which is in the graphic below, which states that the number of transistors in an integrated circuit would double every 2 years. I also expected that games and graphics on computers would get more and more realistic, but I would not have anticipated the rise of smartphone or tablet computing, as the cell phones that we had around when I were a kid were the Nokia 5510 and 3310, the bricks that are practically indestructible. We did have VR when I was a child, but the only VR that I had exposure to would have been Nintendo's Virtual Boy, which I personally didn't find very appealing as it was stationary and you couldn't move with it like modern VR headsets. You basically had to sit it on a table and you had to put your head inside the VR headset, and it was pseudo 3D. It was completely in red, and as interesting as it was not very impressive, at least to me. Requirement 3A. How are text, pictures, and sound digitized for storage? So we're going to first talk about text. So when we talk about digitizing something, we talk about converting it into a form that the computer can read. Computers read using binary code, which is a series of ones and zeros. This is represented in memory as a switch that can be turned on, which represents 1, or off, which is 0. A single 1 or 0 would be called a bit, and they are typically arranged into groups of 8 bits, called a byte. A byte can typically store a single number, letter, or character. Put enough bytes together and we can store words. For example, if we wanted to store the word scouting, we would need 8 bytes, or 64 bits. And as you can see in the slide, the word scouting is represented in binary code below. And you can tell it's not very efficient, like reading-wise, because it's taken up a lot more room. But it is something that the computer can read very quickly. To move up to the next level of storage from a byte, we would need 1024 bytes, since binary is a base 2 number system. 1024 bytes is a kilobyte. 1024 kilobytes is a megabyte. 1024 megabytes is a gigabyte. 1024 gigabytes is a terabyte. 1024 terabytes is a petabyte. And it goes on, as there are terms beyond petabytes, but we won't experience those in our daily lives for probably a few more years. Pictures are digitized using their respective colors in a grid layout. As an example, I made this house on pixelart.com, and it is 16 pixels by 16 pixels. Each square you see is an individual pixel. Computers usually store color data in RGB format, which is red, green, blue format, with ranges from 0 to 255 for each of the colors in a series of 24 bits. That's where we get 24-bit color from, and 24-bit color is often seen as having enough data to make photorealistic images on computers. So to digitize sound, we have to convert it from an analog signal into a digital signal. So in a digital audio system, an analog electrical signal representing the sound is converted with an analog to digital converter, or ADC, into a digital signal, typically using pulse-code modulation. This digital signal can then be recorded, edited, modified, and copied using computers. For playback, a digital to analog converter, or DAC, performs the reverse process, converting the digital signal back into an analog signal, which is then sent through an audio power amplifier and ultimately to a loudspeaker. If an audio signal is analog, a digital audio system starts with an ADC that converts an analog signal to a digital signal. The ADC runs at a specified sampling rate and converts at a known bit resolution. CD audio, for example, has a sampling rate of 44.1 kilohertz, or 44,100 samples per second, and has a 16-bit resolution for each stereo channel. Analog signals that have not already been band limited must be passed through an anti-aliasing filter before conversion to prevent the aliasing distortion that is caused by audio signals when frequencies higher than the Nyquist frequency, which is half the sampling rate. As you can see in the image, the samples are the dots, and the analog audio sound wave is the red line. So as you can see, as it gets sampled, it takes just like a snapshot of that analog signal in a period of time. And you take enough of those and you can reproduce the sound digitally. Requirement 3B, lossy versus lossless data compression. An example of lossy and lossless formats would be in audio files. WAV files are pretty large in size, but they are lossless or uncompressed formats. Similarly, there are other codecs which are also lossless, such as FLAC, which is the Free Lossless Audio Codec, and ALAC, the Apple Lossless Audio Codec. There are also some software codecs that can reduce the file size of the audio file, removing some of the information that is harder for humans to hear. These are called lossy or compressed formats, and some popular examples include MP3, MPEG-1 Audio Layer 3, or MPEG-2 Audio Layer 3, and AAC, Advanced Audio Coding Files. Requirement 3C, describe two digital devices and how they are made useful by their programming. I'm going to go simple with the devices I choose. You may choose something else and figure out how it works to tell your counselor. The first digital device I'm going to describe is a simple digital watch with an LCD face. It has buttons on it that allow you to set the time, the date, and also use a stopwatch function. Without these buttons, the programming features would not work. And without the programming features, the watch wouldn't be able to tell time or date, and it wouldn't function at all. The second device I'm going to describe is an iPhone. I'm not going to get into whether or not Android or iPhone is better, but iPhone is what I personally have at the moment. It has a power button, volume buttons, and a silent slider. It also has a USB-C charging port, which is one of its more exciting features to me, which means less cables for me to have to carry around. And without its programming, an iPhone is just a shiny bit of metal and glass that feels good in the hand, but can't really do anything for you. Programming is what makes it work and what allows you to run iOS apps and do all the cool things that you can do on a smartphone. Requirement 3D. Discuss similarities and differences between computers, mobile devices, and gaming consoles. The similarities between all three is that they all have a central processing unit or CPU, random access memory or RAM, and storage, either a hard disk drive or solid-state drive for PCs, and solid-state drives for the newer consoles. You can play games on all three devices as well, though some have more capabilities than others. The biggest differences between all of them is their ideal use case. A computer is really good for getting work done. As an example, this video was written and shot using the Mac and an iPhone and was edited on the Mac. Computers can also be very good at running video games, and running mods or modifications of games is something that a PC can do really well that a gaming console would not be able to do. You can also play games on a mobile device. When I think of mobile devices, I typically think of a cell phone, tablet, or Nintendo Switch, but now we have the Steam Deck OLED, And there have also been several iterations of gaming phones from Asus, so it's gotten a little more expansive. And as the average price of a cell phone gets to $1,000, we're expecting these devices to last multiple years and without breaking down on us. Which brings me to another difference. You can upgrade most Windows PCs and add more RAM, a newer video card, more storage, and even a faster processor depending on your motherboard. You cannot say the same for most mobile devices, especially Apple devices, as they have been designed to only be worked on by professionals, and at a pretty hefty price tag if you do not opt in for their Apple Care. It was only with the recent generation of gaming consoles that you could easily expand the storage on them, with the Nintendo 2DS and 3DS excluded. And even then, only PS4 and PS5 and the Nintendo Switch allow you to expand the storage, with the PlayStations allowing you to use a higher quality storage medium that is faster, an NVMe SSD, than what the Nintendo Switch allows you to use, which is a micro SD. And yes, I know you can upgrade the hard drives on Xboxes, but it is a complete pain to do so. And you practically have to disassemble the Xbox, and you can really tell they didn't want you touching that hard drive. Whereas on a PlayStation, you undo a screw, you pull the hard drive out, you can swap it out, and then they have a program that you can use to reinstall the OS onto the new hard drive. So it's kind of a night and day difference between how you can upgrade a hard drive on an Xbox versus a PlayStation. And of course, the Switch doesn't even give us that option. We just have micro SD cards. And so if you get a fast enough micro SD card, it's comparable to like eMMC memory. Not very fast, good enough. So that's kind of where we're at with the comparative similarities and differences. Requirement 3E. What is a computer network? And then what is the difference between a LAN versus a WAN? A computer network is any kind of communications pathway between two computers. A LAN, or local area network, is when a bunch of computers or electronic devices are connected to the same router or switch, or they're connected to other routers and switches which are connected to the other routers and switches. But the general idea is that a LAN is in a single location. A pretty easy example of a LAN is your home network. You might have cable internet with a cable modem router combo, or a fiber connection with a modem router combo. Every device that is connected to your home Wi-Fi is part of your local area network. A WAN, or wide area network, is a network that covers a large geographic region and can consist of multiple local area networks. For example, a university that has multiple campuses could be considered to have a WAN. Requirement 4A. What is a software application, and how does CPU and RAM execute it? A software application is a bunch of code written in a programming language for a specific purpose that can be understood on the platform on which it is running. You would run the program or tapping or clicking the application icon, and then the CPU would begin its fetch, decode, execute cycle. And we're going to explain this in further detail. It gets kind of complicated. So, in our fetch phase, a memory address in the program counter, or PC, is loaded into the memory address register. The program counter is incremented to point to the next instruction. Then the instruction is found at the address in the memory address register and is loaded into the memory data register. The instruction in the memory data register is loaded into the current instruction register. And that's the end of the fetch phase. Now we go to the decode phase. The control unit decodes the contents of the current instruction register. And then we go to the execute phase, where the control unit sends signals to relevant components according to the instructions in the current instruction register. And then the process is repeated over and over and over again. So this one little fetch, decode, execute cycle is just one cycle of a computer's instruction cycle. And it does this millions of times a second. The RAM is used for short-term storage for the CPU so that the computer can keep your program in memory, which allows you to use it until you decide you want to quit the program. Once you quit the program is removed from RAM in a general sense. Some modern applications will keep a service running which is a different name service than what the application is, to check for updates, phone home, do telemetry, all the fun stuff. Requirement 4B, name 4 apps your family uses and explain how each helps you. So we use WhatsApp, and it allows my family to stay in communication with one another. It's especially useful because I have Android and iPhone users in my family, and so I get all the features of a rich communication chat service like iMessage or Facebook Messenger with WhatsApp, and we can react and send stuff, and it's not going to be reduced in quality like if we were still texting. We also use Apple and Google Maps. It allows us to monitor traffic on our commute to my son's school and to work and on the commute back home. I use an application on my Mac called Magnet, which allows me to pin windows to my MacBook screen, similarly to how Windows 10 and 11 handle window movement and app pinning. And then I use something called Bitwarden, which is an open source password manager. It allows me to not have to reuse or remember passwords, and it's free to use, and it's very helpful because you just have to type in your master password or a PIN every time you need to use a password, and it can generate all sorts of neat passwords for you. It can also generate usernames for you as well, especially useful if you want to be as private and anonymous on the internet as possible, which is becoming more and more of a concern these days. Requirement 4C. Describe what malware is and explain how to protect your digital devices and the information stored on them. So malware is software that's been coded to steal personal identifiable information and or destroy your computer, or in more recent cases, to use your computer's idle cycles to help mine for cryptocurrency. Some of the best ways to protect your device are to never download files from an unknown source, never click on links in an email, chat, or on social media unless you know, trust, and have verified that the person who sent you the link is actually the person you think it is. And also, use an ad blocker. Ad networks do not scan their ads, and sometimes those ads can contain malware or drive-by download that can infect your machine and try to take over and just make your life miserable. So I always use an ad blocker when I'm browsing the web. It's not because I'm trying to take revenue away from companies that need it. If it's a company or a website that I trust, I will turn the ad blocker off. But for majority of websites, I don't trust them. And so I don't want their ads to be loaded onto my machine where they could potentially infect it with malware. Describe 2 different ways data can be transferred through the internet. So the 2 ways I want to focus on are client-server and peer-to-peer. So the example of a client-server interaction is when you go and visit a web page, the server sends your PC, which is the client, the data about the web page, and then your web browser interprets that into a website that you can see. And then typically your PC will send information back to the server to request like another page from the server, and that process will kind of repeat. As for peer-to-peer, I'm going to use the example of a local area network. So if you're on a local area network and you have a file and folder sharing turned on your Windows computers, you can remotely access other PCs on your network, and with the credentials of that other PC, you can log in and remotely transfer files from that computer to the computer you are currently using. So for requirement 5B, we're supposed to do an internet search for a Troop Court of Honor or Campfire program. So I went ahead and screen recorded myself going to a search engine and doing a web search for a Troop Court of Honor. And so I'm going to kind of talk over it as I go through this video. So I look up Scout Court of Honor Ceremony, and I choose a couple of the resources that I've found. Ironically, I do end up choosing one of the parent sites for the first link that I clicked on, so I really only have 2 sources, but you're supposed to have 3. But that's okay, this is just for example purposes. So then I open up all 3, and you're supposed to show your counselor what you found. So this is what I'm doing. I'm showing you guys the 3 websites that I found. That's basically what I'm doing for this requirement. So on this requirement, we're going to use a web browser to visit an HTTPS site, and the site that I chose is duckduckgo.com because it's privacy focused. So we go to the website, we click the little lock in Safari, and then it will show you the certificate that this website is signed by, and it also shows you the certificate chain, which is the 3 layers of certificates that you see. You see me scrolling through the DuckDuckGo web certificate that is only good for a few months. And then as I go up a layer and then up another layer, the expiration goes out by years. And that's just to let you know that like the root certificates are signed, they're good for a long time. And this is how HTTPS certificates work. And this is how you know you can trust the site, because it's been digitally signed by a different authority that lets you know this site is secure. Requirement 7A. Explain to your counselor each of these protections and why they exist. Copyright, patents, trademarks, and trade secrets. Copyright exists so that creators can get attribution and payment for things that they create. For example, books, music, and movies. They're used to protect a created work. Patents do the same thing, but they're used to protect ideas and discoveries. Trademarks are a type of intellectual property, and they depict a sign, design, or expression that identifies a product or service and distinguishes it from the others. So some examples of trademarks are like Just Do It from Nike, or the Scout emblem for Scouts BSA. Those are trademarks. Trade secrets are ideas, formulas, practices, and patterns that have economic value and are not known or generally ascertainable by others, which the owners take reasonable measures to keep secret. From Wikipedia, intellectual property law gives the owner of a trade secret the right to restrict others from disclosing it. So some examples of trade secrets are like the 11 herbs and spices of KFC. Requirement 7B. Explain when it is permissible to accept a free copy of a program from a friend. The short answer is that it is only acceptable when the friend buys you a copy of the program as a present from a legal source, like Steam, or they give you software that the creators have allowed you to download for free from the internet. There are multiple kinds of software on the internet. We have free software, paid software, open source software, and closed source software. So what does open source and closed source software mean? Generally, open source software is software where its source code is freely available to download and inspect. Closed source software is just the opposite. The source code isn't available to download and inspect, and you must trust the publisher of the software with what they have written. You cannot inspect it yourself like an open source software. Now, I know some of you might be like, who has the ability to pour through lines of source code anyway? But it is helpful, especially in a world where we have malware and software that tracks you to sell your anonymized data to advertisers for their own benefit, to have options like open source software that we can use and we can trust and know how they're running. Requirement 7C. Discuss with your counselor an article or a report on the internet about a recent legal case involving an intellectual property dispute. So, the article that I looked up, which was current at the time of recording, which is March 7th, 2014, or 2024, is an article by Blake Brattain on Reuters website called Google Hit with $12 Million Jury Verdicts in Google Voice Patent Case. So this article talks about a patent dispute between Flip Technologies and Google, where a court has decided that Google Voice has violated patents owned by Flip and has been assessed $12 million in damages. Google alleges that the technology used in Google Voice was developed before the patent was filed, and they're planning to appeal this verdict. So as you can see, the patent violations happen all the time. And I'm sure when you're watching this video, if you do a search, you'll see that there'll be a recent patent or legal dispute within the few days of when you watch this video. Requirement 8A. Describe why it is important to properly dispose of digital technology. List at least 3 dangerous chemicals that could be used to create digital devices or used inside a digital device. So why is it important? Digital devices have rare earth minerals in them that are non-renewable and are in a finite supply, which means we will eventually run out of them. They're also expensive to produce, and so recycling digital devices is one of the biggest ways we can reduce the risk of running out of these materials. And then the 3 dangerous chemicals used in digital technology, or the 3 chemicals that could be inside a digital device. We have cadmium, which is used in rechargeable computer batteries, mercury, which is used in LCDs of computers and mobile phones, and nickel, which is used in some mobile phone circuit boards. Requirement 8C. Do an internet search for an organization that collects discarded digital technology hardware or devices for repurposing or recycling. Find out what happens to that waste. Share with your counselor what you found. So I did a search for an organization that recycles digital technology, and I got to the Consumer Technology Association Greener Gadgets page, and they have something called a recycle locator that gives you all sorts of different organizations in your local area that will recycle electronics. So from the Consumer Technology Association's Greener Gadgets recycle locator page, I found an example. So we have Staples. So what Staples says is that they recycle all this tech, and that they go and reuse it and sell it to other companies to make new products, and then those products get resold as new products. Requirement 9A. Careers in digital technology. Investigate 3 career opportunities that involve digital technology. Pick one and find out the education, training, and experience required for this profession. Discuss this with your counselor and explain why this profession might interest you. So I have 3 options here that I looked into, and I've been 2 of them, and in some instances all 3. So my current job is as a business intelligence analyst, and the things I do for my job on a day in, day out basis are I'm in Excel looking at spreadsheets, generating reports that way. I'm also using Python, and I'm developing regression models to determine what things we could potentially do to improve or to predict an outcome for my job. In the past, I've been an IT manager, so I managed servers and infrastructure and computers, and I was also helping users learn how to use their computer and just troubleshooting it, fixing it, repairing them. And the amount of education and training for these kinds of jobs, you'll want to have at least a bachelor's for an IT manager or software developer position. Typically, you want it in computer information systems or computer engineering or computer science. A master's degree is helpful. I have a master's degree in business analytics, and that helps me a lot in my business intelligence analyst role at my current job. And I've thought about going for a doctorate, because they do have doctorate level courses for information technology, and a lot of those are in the engineering space, but there's also in the statistics space as well, and that's where data scientists come into play. Those are the kinds of people that they're analyzing lots and lots of raw data, and they're using something like Python or Tableau to analyze that data and turn it into information and a story that can be used to help promote whatever that they're trying to do. Well, if you've made it this far, you have successfully completed almost all the requirements for the Digital Technology Merit Badge. Or at least you now have an understanding of how to do these requirements so that you can tell your counselor what you've done and how to do it. So here at the end, I'm going to have a few slides of my sources. where I got this material. Most of the material came from Wikipedia because it's a source that nowadays can be very trustworthy. Back when I was a kid in high school, the early 2000s, it wasn't considered trustworthy at all because anybody could edit it. But now they have such good editors at Wikipedia that if you were to vandalize a web page, vandalize an entry, they would be able to revert it almost immediately, and then also just ban your IP address so you couldn't make any more edits. So that's why I used Wikipedia a lot for a lot of my sources. There's a really cool website called computerhistory.org that kind of goes through the changes in digital technology in a lot more depth and a lot greater detail than I ever could, especially since I was supposed to give a brief introduction to the history of digital technology. So I encourage you to visit that website. And then thank you for your time, and I hope you have a good day.